My pleasure. Thanks very much for the invitation. Because it's this audience, I had a really hard time picking any of the topics. So what I'm going to do, I hope I'm not killing you by doing so. I'll give you an overview of what we do, and I hope it's not too fast, given the time of the day, food coma and whatnot might affect you. Interrupt me if any time, of course. So I'm going to show you how we can control electrons with light, with really phase-controlled laser beams, also with non-classical light. And I'm going to show you how we can control free electrons that are emitted from these needle tips, or free electrons that propagate through nanostructures, but also electrons that are in certain materials, and I will focus on graphene here. And it's all based on really transferring the level of control we have these days on these laser pulses, and trying to see what we can do. And what's so nice about this level of control we have over these laser pulses is that the time scales are such that the electrons behave fully coherently on the time scale of a femtosecond. If they're free, that's probably easy to see because they're free, they cannot really interact strongly with anything, but it even holds for room temperature graphene, which is known to have extremely fast dephasing timescales, yet these dephasing timescales are longer than the timescales we need to play some fun physics with these electrons. Let's start out by telling you where we are. You know, there's the dreadful Röthenheim Creek here in between. Not so sure if you ever dared to cross this bridge here, but if you did so, you just make a left and this is where we are. Very close. You're always welcome, of course, to come over. And with that, let me start out with the first topic, and I have to start out with this topic here at this particular institute because these structures are made here, and I'm very happy to see Olga. We have fantastic support from MPL Cleanroom. I'll show you in a second what you see here in a nutshell. These are 40 accelerators. The details you can't see in an optical microscope image. The details is, of course, also interesting on the nanoscale, but this only works because of the fantastic cleanroom and the fantastic cleanroom team. So this is for you, Olga. Hold on, there it is. Here we go. Why do we want to shrink particle accelerators? You know these big machines, why they're so big? They're so big because to generate a certain final energy of the electrons, you need to be able to accelerate them. And the larger the gradient, the larger the final energy. So it's really the gradient that determines the size of the machine. So if you want to do Higgs spectroscopy, so you want to generate particles above 1 TeV with today's gradient, which we stand at now after almost 100 years of accelerator physics, with just 30 mega electron volts per meter, you can just do the math yourself. It's a 30-kilometer long machine. So if you want to do this here on campus, it would be great if we could just get this number up by a factor of 100. And this is doable with light, but there's something much more important because there are also these accelerators that you all know that scan around the body of a patient. They're L-shaped because there's an accelerator inside here, 1 meter long. Why 1 meter long? Because our friends in the radiation hospital needs sufficiently energetic X-rays, and for this they need to accelerate the electrons to roughly 20 MeV. You take the number, roughly 30 mega electrons per meter, you end up with a 1 meter long accelerator. And our dream is take that thing, shrink it by a factor of 100, and have a new device for intraoperative radiation therapy and whatnot, based on lasers. This is how all accelerators work. It's exactly like this surfer here, surfing the wave. If the electrons have a certain speed, you can phase match them with an optical mode, and then the electron just surfs the mode. And if you just accelerate the mode, you accelerate the electron. This is the very principle of any RF accelerator. You can have field strength as large as 200 million volts per meter, very large field strength, at RF. That's why people go to RF. Then you have gradients at your disposal. There's just this number times E, so roughly 100 mega electron volts per meter. Divide that by 3, and this is how you build an accelerator. You don't want to build the accelerator right at the scientific limit, of course. But you all know you need very, very powerful laser beams to damage glass. And that's exactly the driving force for our miniature laser accelerators. This is glass or silicon or whatever you wish. It's a structure that also generates this mode over here to accelerate electrons. And we only need a phase grating, so it's just something transparent that shapes near fields so that you can accelerate electrons. Damage thresholds are roughly a factor of 100 larger if you go to optical frequencies and dielectrics, so transparent structures. And this factor of 100 is what we want to take advantage of. Then you can have factor of 100 larger gradients, then your accelerators can be shrunk by a factor of 100. And I want to show you where we stand, because this is something really interesting. How does it work? The very principle is probably clear to everybody in this room. If you take a diffraction grating, right, this is just a grating, and you shine light, you can generate, of course, zeroth order mode just go through, then you can have plus minus first order, but this plus minus first order doesn't need to go under an angle like this, it can also go under an angle of 90 degrees. And this mode that then propagates along the surface, that's the mode that we use to accelerate electrons. It's very simple, it's just diffraction if you want, but this mode that propagates along the surface is a near field mode. So it only lives in close proximity of the grating. That's why you see here the colors decay very quickly. That's why we have to bring the electrons close. And the decay length, like for any evanescent field, is roughly given by the wavelength of the driving light. So these structures have to be small. They have to be shaped on the size of the wavelength. But that's the very principle. And this is what we could show in the last 10 years or so, that we not only can accelerate, we can also steer the beam, deflect the beam. We can also have the beam interact at one laser interaction region and another. We can also exert transverse forces to focus the beam. And that's very important to build accelerators, not only to just accelerate the electrons, but also hold them together. But even then, you don't have an accelerator. You really have to take beam dynamics into account. So you want a structure like this that really steers the electron beam through this narrow channel. This narrow channel is basically just two gratings opposing each other, and we just etched away the glass behind the gratings, and we made the pillars round. But this is basically nothing but these gratings that are there to accelerate or to generate this mode that then does the acceleration. Sure. It'll come in a minute. Thank you. This is how these structures look like. This is what we call dual pillar structures. Electrons are injected from the left. And then, just to answer your question, Wahid, we can shine the laser from the side, we can shine the laser from on top. Once you have such a structure with the right periodicity, you basically just have to get light on it, and you get this mode generated. But there'll be more in a minute. And then there are these trenches, and what I really like to show you in the next couple of minutes is what are these trenches for. This is something I think really beautiful physics. I don't have time to show you what our friends at Stanford did. They also have these acceleration structures, and they already powered them with on-chip photonics. That's of course really cool. If you have on-chip photonics to do the job, then you can really integrate this, just maybe even put the lasers here and power the structures this way. So how does it work? This is we're a physicist, so we have to go a bit into detail here. Just want to show you this because it shows us the force acting on a particle that you inject here. That is already synchronous. So the electron's speed is matched to this mode that we generate here, which is color-coded here and here. And I'm showing you two different components. This color code here shows us the forward component of the force. It's just a Lorentz force, written slightly different. So here we see electrons are accelerated, decelerated, and so on. Over here is the transverse component. This one here is always there when this is there, but of course I can't put them on top of each other, then we can't see what's going on. The nice thing is, this one we use for acceleration. This force, these transverse forces, we use for beam confining. And now there's one important figure here, and that you can just solve Maxwell's equation yourself. You get this sine and cosine here, which just tells you that these two fields here, the maxima of this field and this field here, are 90 degrees out of phase, which leads you to this situation. You have, this is showing the transverse force acting on a particle, maybe down here. This is the simultaneously acting forward force. And here you see something interesting. Here you want to be on the forward force component somewhere here, because then you get forward acceleration. The particles that come later see a larger force than the ones that come earlier. That's good, that keeps you bunched together. So you want to be here. Unfortunately, here, you have a force that drives a particle that is slightly below the center line, further away. So this transverse force now is exactly at a phase where you don't want to be, because it basically just decollimates your beam and just makes the electron crash into the structure. So from the transverse force perspective, you want to be somewhere here, because it just means when a particle is slightly below the center line, it experiences force back towards the center line. So from the transverse perspective, you want to be here. From the acceleration perspective, you want to be here. What do? Well, you just toggle between these two positions. This is what people know in accelerator physics since Courant and Snyder. Maybe you've heard of Courant-Snyder physics. This is Courant-Snyder physics. You can show that you can have a stable beam when you just make the electrons experience this force, these forces for a certain time, and slightly later these forces for a certain time, and then you always hop between here and here. And this gives you stable beam confinement, both longitudinally and transversely. How do we do this? We just dial little phase jumps here in our pillars. So the electrons propagate down here with a more or less given speed, and then you just have a little phase jump here, so the electron just enters now a near-field region that is slightly phase shifted with respect to this near-field region here. Phase jump here, phase jump here, phase jump here just means you basically jump here between these 2 points. Does it work? That was a big question here in this very institute. We made this beautiful structure here a couple of years ago, where we have these gaps in here that do the phase jump, and this is. I don't want to bore you too much with data. Of course, please feel free to ask questions. We just see that we get more electrons, up to a factor 3 more electrons through when the laser is on. Then we get active beam confining. You see here the electron beam is somehow breathing through this structure. You don't see what happens longitudinally here, not so important. But we have active beam confinement in a channel that is just 200 nanometers wide. Very narrow channel, and we get the electron through. If you overdo it, if your fields are too strong, you basically give an electron that comes in here too high kick up, it crashes here, so you can also actively kill your beam. But if you do everything right, you have active beam transport. And in accelerator physics, everybody tells you transport comes before acceleration. If you get your accelerator LHC or whatever to just circle the electrons once around, you basically won, because then you've proven that you can transport your beam. Now, we want to accelerate, but this was the important one here, because it shows us we have 10 phase jumps, one every, this is so interesting, right? In the frame, co-moving with the electrons that propagate down here with 1/3 of the speed of light, 30 keV electrons. We have a phase jump every 76 femtoseconds. Requires high fabrication accuracy because phase errors would add up. But definitely, if this works, we have really, for the first time, complex electron phase-space control at optical frequencies. And it works. I showed you the data. I would just want to take you to acceleration right away. Now, we want to accelerate the particles. Sure, please.
What's the significance of the lamellas?
You mean here? Sorry, this here? This is a Bragg mirror. So when we shine the laser from the side, we only need one laser beam. We place this Bragg mirror at the right distance, so the light that is back reflected adds up in phase here. So this is just a Bragg mirror like you know it from a dielectric mirror. You can just have these slabs here. These are lambda over 4 spaced, and you get the light back. And if the distance is right, the fields just add up. Height. This is where everybody's envying us. When you get the top view, when you show them this one here, hold on, where is it? This one, so yeah, sure, we can do that, no problem. Then you show them the side view, and then everybody's asking you, so this one here, for example, ooh, that's pretty high, that's 3 microns, 2 microns, 3 microns high, gaps only 200 nanometers, the famous aspect ratio that everybody, or pillar diameter, roughly 200 nanometers, aspect ratio more than 10 to 1, that's tough. That's what my students, Payman Yosefi and Julian Litzel, had to develop together with Irina and her team. I'm not aware of any other clean room that can do these structures. I'm sure they can develop the process, but this was basically one PhD thesis to develop this. So thanks for that question. That's important for us. Yeah.
So you come with a cylindrically focused.
It'll come in a minute. You'll see it in a minute. When we go to acceleration, then we come to the really long structures. Here you now see a slightly different graphics. The forward force. So we want to always see the electrons accelerated and ideally bunched, so the later ones see a larger field than the earlier ones. So this is where we want to be in forward force. Then you saw it in the only equation I showed you. Then we're transversal force is defocusing. Now, when we go to acceleration, we want to have a phase jump, so that we are transversely focusing, but we want to still have the electrons experience accelerating forces, even if they are debunching. So even if the early electrons see a larger force than the late ones. Doesn't matter. They should always see an accelerating force. And then you have now phase jumps that are 120 degrees and 240 degrees. Then the electrons always experience accelerating forces, and we still toggle between transversely focusing and defocusing, and it could still work with acceleration now. This is what our simulation tells us. You again see how the electrons breathes through the structure, and you see the changing color code, which shows you that the electrons gain energy from roughly 30 keV to 40 keV over half a millimeter. For people versed in accelerator physics, this is what people call a photolattice, focusing, defocusing, focusing, defocusing, but all the time accelerating the electrons. If this works, that'll be fantastic. Here's how these long structures look like. You see these trenches, big trench, small trench, big trench, small trench, and so on. We have up to 0.5 millimeter long structures. These are now 733 pillar pairs. The position of each and every one has to fit to less than 10 nanometers, of course. But we can discuss the details later. This is how these structures look like. These are the shortest one we made, 100 microns. This was what's in the circle. It was the previous generation. And of course, we were courageous. We thought, okay, let's also try 200 microns. And maybe if stars align, 300 microns might work. And I don't know if what else aligns, also the longer structures could work. And here's what we do. So the electrons come in like this, and then we have this pulse front tilted laser beam. Here's the answer to your question, Vahid. We focus cylindrically, but we also have to have a pulse front tilt. Why, you see in a minute. These are the different structure lengths, and then this is how it looks like. The electron always feels the peak of the laser if the pulse front tilt is matched to the electron position, which in first approximation works if we just assume that the electron doesn't gain energy. But of course it does. So ideally it should be a pulse front banana, but we have not been able to make one of those. Here's how this looks like, what we saw that. This is what should happen. This is what's the energy gain as function of distance where the electrons is in the structure. This is the design curve. Most of the electrons are lost. But some should be captured. This is this famous bucket of particle acceleration. And here's what we measure. 4.5 eV in a 200 micron long structure, matches perfectly what we would expect. 300 micron long structure, 6.6 peak at 6.6 keV, matches close to perfectly what we expect. 400 micron, 500 micron, all the structures worked. We were really limited by structures, which is, of course, what you want to have. Fantastic. That's roughly a year ago that we saw this fantastic result, that we see electrons exactly, or more or less exactly where we expect them. And we really seem to have the photonic laser accelerator on a chip working. What was fantastic, our friends at Stanford, collaboration partners, but of course also friendly competition, got exactly the same result, and which was also just recently published. So this laser accelerator on a chip is a reality. We have to get the currents up. We have to get better structures to feed more electrons in. But this is the status. And just to show you one thing, here we also see that the electrons not only interact with a light field classically, but when we measure the energy of the electrons carefully with a resolution better than the photon energy, we actually see that the energy transfer between light and electrons is quantized. So we see here, these are the electrons that basically didn't interact with the laser field. Some of them gained energy, some of them lost energy, but quantized in terms of photon numbers, which is of course great. There's an entire field now which has started with something which is called photon-induced near-field electron microscopy, pioneered in the group of the late Edward Zewal. And now there's this really big group, big field or developing field that is aiming at coherent coupling of electrons and light. We can then also shape the electrons. The electron really, after a while, looks like this here. It's a Gaussian, or not so Gaussian. It's a wave packet, modulated wave packet, and the Gaussian wave packet is then really spatially looking like this here. You can do a lot of stuff with that. Skip this. All right, let me switch gears. Of course, you all know the last physics Nobel Prize given to attosecond physics. And attosecond physics means controlling electrons with an optical field of ultra-short laser pulses. Well, of course you know them, I don't have to tell you. And we basically do very related stuff. We just look at exactly the same physics, not at atoms or molecules, but at these sharp needle tips. So we can get the electrons out, then the electrons really behave as electron matter wave packets. They can interfere, and of course this is all driven by these two-cycle laser fields that interact with these needles. I'm also going to show you something that is very, very recent. A paper just came out together, a nice result together with Maria Chekhova's team, where we used bright squeezed vacuum to trigger electron emission, and you get very, very different electron counting statistics. I'm going to show you. So what do we have? We have now these sharp needle tips, and we have this optical near field that happens here at these tips. It's enhanced there. It's basically the optical analog of the lightning rod effect. And then electrons are emitted and are driven in the field. So this is kind of the macroscopic picture. What happens, the electron can be emitted, and then you all know from the Attosecond Physics Nobel Prize, there's this famous rescattering that then lets the electrons pick up more speed. And this is exactly what happens at the surface of a tip. So this is now time. Electrons are driven away, return, bump, scatter elastically at the tip and make it away. This works with single colors, but very recently we also looked into two-color fields, where we just add up two colors. And now we can do something really interesting. We can vary the yield, the background here. The color shows you the yield, so white means many electrons. We can have, for example, very many electrons when the phases add up correctly of these two colors, but we can also have very few electrons. But then we see that when you look at the color, red here can be very dark red. We can also generate very high energy electrons, or here we hardly generate any high energy electrons. And this modulation that we can steer by varying the phase of these two colors really allowed us to look deeply into what happens to these electrons. And I don't have time to show you in detail. Please feel free to ask questions, of course. We can now record these electron spectra. Here you see this famous recollision plateau. That's what brought Anhuyer the Nobel Prize in Physics, understanding what's this plateau due to. We can record this plateau as function of the relative phase between these two colors. And from these spectra, we can uniquely work out what is the emission duration. Here, let me just sketch you. Here we look at the energy of an electron emitted in one cycle of the laser field as function of the relative phase between these two colors. And we know exactly where the electrons reach the highest energy. We know exactly when the electrons are emitted. And just by really understanding these spectra, we could, for example, measure the emission duration with an error bar of only 30 attoseconds, just purely optically, just by looking at these spectra, which is great because there are people out there who want to do electronics with these free electrons, and this is the first time that we can tell them, yes, it really works. You can have sub-cycle duration electron pulses. This is with a laser pulse duration of something like 5 femtoseconds. This is deeply sub-cycle dynamics that you can really use and steer your electrons. Very recent work is now, I told you the electrons move in the optical near field here, but this optical near field very quickly decays. And this was a real discovery. It was really fantastic. Real discovery we made. All of a sudden we realized, hold on, so these are these recollision spectra again. This is this famous plateau. This is the cutoff. And here now as function of the carrier envelope phase. So you all know when you have very short laser fields, 2 cycles, so it really depends where's the maximum of the optical field with respect to the envelope. This is the carrier envelope field. And we saw some very clear stripes here, which nobody had ever seen before. Scratching my hands, what's going on there? And Jonas Heimer and Stefan Meyer worked it out perfectly what these stripes are. And it's really just the electron dynamics in this near field. So the electron is now being driven away from the surface where the field gets smaller. Then the laser field flips around and drives the electron back, but already with a smaller amplitude. So we have to take into account this weird coupling of spatial amplitude drop and basically quiver motion of the electrons. But this could nicely explain everything. So this is really just a very simple simulation where we can explain these spectra here. We call them near field induced low energy stripes. New spectral features are always fantastic. This one spectral feature, namely this featureless cutoff, brought Ferenc Krauss the Nobel Prize. Not claiming that this is Nobel Prize worthy, but you never know where things are going, of course. Keep fingers crossed. But this was really great to see this new spectral feature here that only arises because of the near field. So you cannot observe something like this with atoms or molecules. You only have it because there's no subcycle near field dynamics. And let me come to another point. So far, we only looked at individual electrons driven in the field. What about two electrons that are emitted here, this very sharp needle? Will they interact? Will they repel each other? So we had a new detector, and we thought, let's look into correlations of these electrons and really detect position and energy of each and every electron that arrives here, also when there are more than one, so 2 or 3 electrons in one, emitted by one laser pulse. And this works because of this new detector. Suffice it to say that when we look at 2 electron events, we see something very interesting. We see this here. When the first electron has a most likely energy of, say, 41 eV, the second electron's most likely energy is 39 eV. This is how you can read these plots. And then the same data are basically mirrored up here so that you can nicely see what happens at the diagonal. And at the diagonal, where you would probably, if you didn't have any correlation, you would expect most electrons on the diagonal. We see here there's hardly any electron at the diagonal. So we see very strong anti-correlation effect in the energy. When you integrate this up, you see that the electrons are most likely spaced by 3 electron volts. That's a huge number that you can really use. You know that the energy width in electron microscopes is typically 0.7 eV, in field emission microscopes 0.3 EVs. This is much larger than the energy width of the beam. This is something you can use. You can use heralded imaging now, which we know from photons. You can now do it with electrons, and there it's really useful because it's very, very useful to know if an electron is at the sample just because you detect the partner electron, because then you know there is an electron, there has to be an electron. This can really drive electron microscopy quite a bit forward because the samples are so beam sensitive. Here, of course, in this institute, a lot of people are interested in quantum optics, so I have to show you the G2 function, and the G2 function here in this area is much smaller than the one, so really sub-Bosonian behavior here, which nicely works. Sub-Bosonian behavior brings me to something quantum, which is not quantum, but at least non-classical. You all know Marshall Chekhova is world famous for a bright squeezed vacuum, where you just can... Sure.
Before you...
Sure.
So in your G2 function, you're measuring electrons, right?
Yeah.
And what's the rate of electron flow? What's the ballpark?
Great, thank you. So here you see it. We set it to below 1. So you can read it. Well, if you're an expert, you see it faster than I see it. It's probably the red is the Poisson distribution. What is it, 0.3 on average or something? Or 0.1? We don't want many per shot, per laser shot.
Per shot, okay.
Yeah, per laser shot at 80 megahertz.
Okay.
Yeah. That's sizable currents. For electron microscopy, this is interesting. Picoamps. Typically 10 to 100 picoamps. Sorry, this is not at 80 megahertz, I'm sorry. This detector, it's detector limited. The detector doesn't allow readout rate faster than, I believe, exactly 500 kilohertz or so. So we have a pulse picker. But if we take the pulse picker out, of course, we expect the same physics to happen at the laser uprate, and the laser operates at 80 megahertz. Thank you. But this is right. Yeah. This is what we measure when we look at the electrons and just shoot our femtosecond laser pulses at our tips. This is the number of electrons we detect as function of laser pulse energy. We see a nice Poissonian distribution. This is the data points, and the lines are Poissonian distributions, no fits, but Poissonian distribution for this mean number of electrons fits perfectly. This is what happens when we shoot Maria Chekhova's bright squeezed vacuum at the tips. We see the most likely event is still 0 electrons per pulse, but we get up to, 55 electrons per pulse. Even for this, so for the same pulse energy, the probability to see 55 electrons over here with the Poissonian distribution is 10 to the minus 120. So forget it. Likelihood is 0 to observe these outliers here. So you see this very strange statistics that we can just imprint from the light onto the electrons. That's so interesting. So the electrons inherit the quantum statistics of the light. Of course, the question is, does that also work in the other direction, where we have the number squeezed photon states? What about the number squeezing of the electrons? That could of course also be very interesting. We have to see, we have to work it out. Last topic, last 10 minutes. Just sketching you, as you can see, what we can, please.
I'm asking a question, maybe
Great.
because you changed topics, so I think it's a little easier to ask questions.
Thank you, sure.
So, is the process such that there is an electron per photon? Because if that is, then everything else is kind of straightforward, right? But what is the relation between?
Thank you, perfect. That's an excellent question. You see here, when we look at the slope, in both cases, this is the pulse energy, and this is the mean number of electrons we get out on a semi-log scale. So the slope gives you the exponent. And like we would expect, this is a, okay, sorry, I'm not showing it here. This is a multi-photon process. You need, the slope tells you right away how many photons you need on average to get one electron out. So the electron needs to be promoted in energy by the absorption of 4 photons. So it's not a single photon process. That what makes this so interesting, I think. So we'll see, which also means you could, it might be really interesting to consider what kind of number squeeze states do you want to shoot at these tips so that these results get really interesting. Yeah, thank you, thank you. Let me show you in the last 10 minutes or so what happens in graphene and what's happened at this graphene gold interface when we shoot laser beams here. And I think it's also beautiful physics. You all know you know Rabi physics. We think of two-level systems. In solids, we have usually 2 bands. So this is K, quasi-momentum. So you have an additional variable where you don't have just a two-state system, but 2 bands. So when you now crank up your field strength, something very interesting. Well, okay, here, when we have resonant transition, we can think of the light in terms of photons. When you go to strong fields, something very interesting happens. You can drive what people call intraband motion. So the light field can just wiggle the momentum of the electron. And then when the electron comes in here with a certain momentum, it can undergo a transition. This is the Landau-Zener transition. So you can have excitation from the valence to the conduction band, also for non-resonant light. And that makes this so interesting, that non-resonant light via intraband motion can drive interband transitions. It's very, very different physics than Rabi physics. Fun physics, fun to explore, and we explore it in graphene. You know, this hexagonally arranged single plane of carbon atoms. If you go to reciprocal space, you get these famous K points in your Brillouin zones where the valence band and the conduction band touch at one point. That's actually not so important for us, but this makes graphene so interesting for many. We don't really care if they touch or not. What's so interesting here, let me just show it to you again, the K vector, so the quasi-momentum of the electron, is now coupled to the light field in a very elegant way. This is what people call minimal coupling, pile substitution, Bloch's acceleration theorem. It's all the same. If you have an initial quasi-momentum that changes when you shine light in this very, very elegant form, where A is just a vector potential of the light field. So it's just a negative time integral over the E field. So if you just know your vector potential, you know right away what your K is as function of T. And then you all know the famous Landau-Zener transition probability, which depends on the band gap. It depends on how fast the electrons are injected to this point here where they can undergo the transition. And now this is now coupled. And that's so fun. And let me show you, this is really responsible for generating light and currents in graphene just by the broken symmetry of the light field. We don't have to go into the details. But I also want to show you what happens at this interface here. Let's look at this once more. This is what can happen when you have a very short laser field. This is now the vector potential of such an E field. Boom, electron can come back here, can undergo a Landau-Zener transition here. Laser field flip sign, boom, it can undergo another Landau-Zener transition here and moves away. So you see, if you have an oscillatory field, sorry, I should point at the field here, but this is then the vector potential of this field. You have 2 times where the electron can undergo Landau-Zener transition up or Landau-Zener transition down. But this is exactly mimicking a Michelson interferometer for light, right? You basically have a beam splitter here. The beam splitter is just the probability of Landau-Sehner for the electron to make it up into the other arm or to stay down here in this arm. And on the way back, you again have the same beam splitter. Electron can go up or can go down. Going up could, for example, mean that the electron goes to the detector. Going down could mean that the electron goes back to the laser. And then you know right away what determines if the electron goes back to the laser or goes up here. It's the relative path difference in this beam split state that the electron has acquired. And then this is exactly the beautiful physics. So we just have to look at the currents. If there's a current, meaning there have to be electrons in the conduction band. If we measure a current, we know there were electrons in the conduction band, and left-right asymmetric, but we can just measure currents and infer how many electrons did we get into one side of the conduction band. This interference is called now Landau-Sehner-Stückerberg-Majorana interference because they all came up with this in 1932, and these later guys even cite the early guys. So almost 100 years ago, publishing was also at high speed. What do we measure? We measure something crazy like this here. We just look at the currents that flow in graphene when we increase the field strength. So we only increase the field strength. What we see is first, current flows to the left, saying a negative. Then it changes sign here. When we zoom in here, you would see that it really starts flowing to the left. Then it turns around, flows to the right. Then it flows to the left again. And here you see that it starts to turn around. So even though we only make the field stronger and stronger, the current direction changes. You think, okay, this is crazy. What is it? Well, it's basically that we drive these electrons further and further in this beam split state here. And the electron just accumulates more phase that then just leads to the outcome of either electrons on the right or on the left of the conduction band, in the conduction band. We can model this, we can take this one step further. I have to show you this. This is a very busy slide, very technical, because the paper just came out yesterday on this. Here is again this interferometer shown, right? This is where the electrons are in the excited state. This is where they're in the beam split in the non-excited state. And the electron measure exactly this energy difference within this beam split state, because this energy difference here determines the dynamical phase of the electrons, right? The phase is just given that the electron has accumulated when it comes back. When we track it here, how it moves here, the further the energy separation, the faster the dynamical phase wraps. This is written here, so we can really measure the splitting here when we just understand what this interferometer is. This is what's shown here. We can just fit the data here and just basically fit the slope of these bands here. The steeper the slope, the larger the energy separation, so we can fit the slope of these bands. Works nicely this way with this interferometer. We can really measure the Fermi velocity or the slope of the bands, and it compares really extremely well. We didn't expect this. People measured with other methods. That was interesting to see that we can really use this interferometer to measure the dynamical phase of the electron. In the interest of time, let me skip this here. I wanted to show you what happens at this gold-graphene interface. Also interesting physics. We also skip this here. I want to come to the end. Just want to show you this is what we can do. We understand what happens in graphene. I didn't show you, we just jumped over it. We also understand that we can generate phase-dependent currents at the graphene-gold interface. We thought, wait, hold on. Now we have two different locations here where we can drive field-dependent physics. Can we use this? Can we use this, for example, as a logic element for ultra-fast computing? And let's just say we encode the logic into the exact shape of this laser pulse and this laser pulse, and then you can quickly work it out that this one laser pulse in the middle here might excite a current flowing to the right, this one doesn't. These two currents eat up. This here only current flowing to the left, or two currents flowing to the left. When you now say, I set my output bit to 1 only when the current flows to the right, this is the logic you get. Only in this case you get logic output 1, the rest is 0. This is a logical NOR. If you want, we can look more into it. You can come up with any kind of logic element when you look at other phases, and experiment and simulation perfectly agree. We really understand what we do, and we think we can now build a logic gate with potentially petahertz bandwidth. What's crazy, my only Outlook slide, and then at the end, Fantastic idea from our friends in Kharkiv, in the Ukraine. They are still there. Sergei Shevchenko and his team, together with Franco Nori at Recon, they realized when you have a material like this, not just with 2 bands, but with 4 bands, you can really use this Landau-Sena-Stückerwerk-Majorana physics to build 2 qubit gates. So you can really use these ultra-fast driven electrons, not at classical bits, but also as quantum bits. What's of course fascinating, because we saw already the electrons are coherent over a certain time scale, and then of course it would be fantastic to also use them as qubits. Found this idea really, really fantastic. That brings me to the end, of course not without thanking my wonderful team, which is most recently shown here. Thank our funders and friends. I should also mention it, I didn't have time to show it, that Francesco Tani is helping us with some new, extremely short, phase-controlled laser pulses. I'm very happy to have his support. I did show you the big fields we work on with light, strong field physics and graphene at the very end, attosecond physics, ultra-fast electron correlations at these needle tips. I've shown you this quantum light electron coupling and photonics-based laser acceleration. I didn't have time to show you our laser development efforts, and I didn't have time that we also control electrons, not with light, but with other means. But with that, thank you very much.